So last time we had a discussion in the class. Well, I don't know if there's discussion, but last time I lectured in the class we were talking about limits, and that was almost a week ago. So let's see if we can remind ourselves what happened. We first introduced the definition of a limit using Calc 1 stuff, Calc 1 functions. And the definition of a limit involved this thing called epsilons and deltas. And I thought about it, and then I thought whether or not to actually dive deeper into the epsilon delta stuff, and then I figured, how many math majors are here? Okay. So maybe not diving into epsilons and deltas would be the better thing to do. But you should still know a little bit about epsilons and deltas. This is how it looks like in 2 dimensions, and we'll try to see how it looks like in 3 dimensions in a few minutes. Oh, this is how it looks like in 3 dimensions. The big difference is that when we have a function of several variables, there's not only the left side and the right side to get to the limit. There's many ways to get to the limit. And so let me see if I can write down the epsilon delta definition of a limit here. We say that the limit as xy approaches x naught y naught of a function is equal to L. We say this if there exists an epsilon, there is epsilon bigger than 0. I'm sorry, not there exists. It's for every any epsilon bigger than 0, there exists delta bigger than 0, such that if I'm wondering if I should use the definition in the book word for word, but I think I'm going to go off and do something a little bit different, slightly different. And what I want to get here is that I'm looking for the distance between the x naught, y naught point and some other arbitrary x, y point, and I'm finding the distance between them. Okay? And I think this will, in a way, this translates back to the original definition. I'll flash back to the previous page, and then we'll take a look at the book's definition of the epsilon delta. So if this is true, then this is true, that the absolute value, and I guess just to be clear, a difference between an absolute value versus a magnitude. This is a distance between 2 points. I'll put double bars there. And this is an absolute value. I'll put single bars here because now I'm going to say that those x, y points that I'm selecting, I'll put that into the function f. And, you know, the result of these functions of several variables is a scalar. And then the L that you're claiming to be your limit. I'm saying that the absolute value of the distance between them is less than epsilon. So first, what I want to do is I want to go back to the previous page and take a look at this definition and see how it relates to the previous definition of just a function of one variable. And then we'll go back to this page and take a look at this definition and how it relates to the drawings. So, for every epsilon bigger than 0, there exists delta such that 0 less than the absolute value of x minus x naught. So that's basically saying the distance between your scalar x and your scalar x naught less than d implies that absolute value of f of x minus L is less than epsilon. Okay, so you see how that is exactly the same as this business. Okay, so it's exactly the same thing. And now, just to retranslate this to how the book defines it, the book takes this quantity here and really just finds the magnitude of the difference. So you subtract those 2 points, you get a vector, you find the magnitude of the vector, and that's how they came up with x minus x naught squared plus y minus y naught squared. So what I want to say is that what they have in the book is essentially, it's exactly the same as how we defined it back in single variable, but now we're extending our absolute value to the magnitude, which is the same as the absolute value. Unless you define it differently, in which case you're living in another space, which you could do legally without. No, never mind. All right, so how does all this look like? We have this drawing here already. So the definition starts off with an epsilon, and well, actually starts off with an epsilon and finding the distance away from L. So maybe could use this picture, but it's kind of small. Let me redraw that picture over again. So I have my surface, z is equal to f of x, y. And then I have my point in my domain. My domain is the R2 in the xy plane, x naught, y naught. And then I have my limit that I'm calling my limit L. And then what I'm saying is that I give you an epsilon that's bigger than 0, and you have to find an appropriate delta for me. So let's let epsilon be bigger than 0, and what you're going to do is you're going to let epsilon be some sort of distance away from L. So what you can try to imagine is that you can create a couple of planes. I don't know. Maybe we shouldn't create a couple of planes. But if I give you an epsilon, any epsilon, what you have to come up with is a delta. So for every epsilon bigger than 0, there exists a delta such that if I make a delta disk around my x minus x naught, so this is delta, and technically this should be dotted because I said the absolute value has to be bigger than 0 and strictly less than delta. So what that means is that I can pick any x value that's not exactly this x naught, y naught point, because if it was exactly x naught, y naught, then the difference would be 0, and I don't want that. And I want it to be less than delta, so I can't be on the circle itself. I want to be inside of the circle. Okay? So if I pick any point x, y, then when you put that back into the function, your f of xy the difference between f of xy minus L, the difference between f of xy and L, the distance between them is going to be less than epsilon. So that means I'm able to contain, with a small enough delta, I'm able to pick any point that I want within this delta disk. And whenever I project it up here, I'm always going to be within this epsilon interval in my z. Okay? So that's the epsilon delta definition. And they have one example in the book, which I was going to give you guys for a quiz. But there's one example in the book that you can take a look at. So I think beyond that, we're kind of done talking about epsilons and deltas. But I think it's good for you to know in case you have a physics or an engineering teacher sometime in the future that really decides to get mathy with you. And the mathy part is the epsilon delta. All right? For more practical purposes, trying to prove that a limit exists is a lot more difficult because we have to use the epsilon delta proof. But trying to prove that something does not exist, we saw that last time. All we have to do is find paths to get to the x naught, y naught that will give us different limits. That's equivalent to where's my example? I thought I had an example here. Oh, that's equivalent to if you have a limit that does not exist back in Calc 1, if you go from the left side and from the right side, you got two different values, then the limit didn't exist, and you could be done. Well, for something that's a function of more than one variable, you have infinitely many paths to get there. You're not just coming from the left and from the right. You come from the left, right, coming from an angle, coming from a curve, coming from a spiral. You're just coming from a lot of different perspectives to get to that x naught, y naught point. And you would have to check all of them to prove that it's true. Or you could just do the epsilon delta. But proving that it's false, all it will take is just one path to show that it's not going to work. Okay? And we started to do that at the end of class on Wednesday. So let's see if we can come up with some more examples of those types of functions. And I guess it would be good to try to figure out how these functions actually look like, especially at those points. I guess before we do that, let's take a look at the set of questions from your book. And take a look at limits. I kind of jumped to limits that didn't exist already, but let's take a look at limits that do exist and see how those things work out. So if we take a look at a function, and when I say a function, I mean the thing that we're taking the limit of, and it happens to be a nice polynomial, or an exponential, or a trig function that's supposedly continuous. We learned that from Calc 1, that it's continuous and differentiable everywhere. Then the limit should exist. And there's nothing else to do but to plug in the points. And so what we do for this, for number 5, for example, limit as x, y approaches 1, 2, of 5x cubed minus x squared y squared. For this, there's really not an issue or question about what's happening. All we have to do is plug in the points. So it's going to be 5 and x is 1. And then minus x squared, which is 1. And then y squared And so there's nothing left to do here other than to figure this out. 1. Okay, so limit does exist and it's equal to 1. Okay. The only times we would have issues with limits is that, if we have the 0 and then the denominator business. That's usually where things happen. So without doing any work for number 6, I have limit as xy approaches 1 comma negative 1 of e to the negative xy times cosine of that. What is this going to equal to? E to the positive 1 times cosine of 0, which is 1. So this is just e, right? So there are no issues for those types of limits. In fact, the limit does exist and it is continuous. And so there are nice limits in continuous function. So we run into some issues when we have zeros in the denominator, but a few of these problems I think we can deal with the zeros in the denominator. Which ones do we want to do?
Let's do the red hot 9.
So when you put 0 in, kind of naively, we're going to get 0 over 0, right? Which is, unfortunately, we don't have a L'Hopital's rule version for 2 variables because we're dealing with 2 variables. So we can't say that the limit does not exist. We can't say that the limit's equal to 0. We have to try to find out another way of finding the limit. What? Even the leading terms are kind of sketchy because there's x's and y's there, and x goes to 0 and the y goes to 0 at different times in different places. So it's a little trickier than that. So what we might be interested in doing is finding paths and hope that the limit does not exist. And so in hoping that the limit that does not exist, what we would be looking for is we're looking for 2 paths that get to the same, to 0, 0, but would give you different limits. So let's check on paths. And a nice path to always check is by setting x or y equal to 0 and seeing what happens. So let's let x equal to 0 to begin with. So we will adjust our limit and change all the x's into zeros. So if x goes to 0, then the only variable that we have left is y. So we essentially trim this down from a limit of 2 variables to a limit with only 1 variable because x is equal to 0. So when x is equal to 0, I'll put 0 in for wherever you see an x. And then the point is that to compute this, you would simplify as much as you can first and then take the limit. So if we simplify as much as we can, I think we'll get an answer of -2. Okay, so that's one path going to 0. Let's take another path going to 0, 0. And the other easy path is when you let the other variable equal to 0. Yeah?
I can't remember, but when you cancel out like that back in the limit stack calculus, doesn't that create a hole?
Oh yeah, there's going to be a hole here in this graph. So the question is it just a hole, or is it something weirder? Is it actually disconnected? Is a question.
And we want disconnected so that we don't have to do like infinite numbers of paths, right?
Right,
Okay.
right. So let's take the limit. Let's let y equal to 0 in our limits. So this becomes a limit of just one variable x going to 0. And we have x to the 4th minus 4 times 0. And x squared plus 2 times, or plus 2 times 0. And then you get the limit as x approaches 0 of x to the 4th over 4, or I'm sorry, x to the 4th over x squared, which also simplifies to x squared. Now if we take the limit as x approaches 0, what do we get? We get 0. And these two are not equal. So we have successfully shown that the limit does not exist at 0. Okay? Yes? For this limit, we say this limit here. So our conclusion, therefore, limit as x, y approaches 0, 0 of this function does not exist. So if it did exist and 0, 0 is not defined, that's when we have this punctured business. And we can put a point here. But here the limit doesn't exist, so it's like it's not even connected, so we can't just put one point in there to make it continuous anymore. So the other thing is, unlike the pre-calculus version or the calculus version of these functions, you can easily see the discontinuity if you're just looking at a two-dimensional graph. For these three-dimensional graphs, it's a little bit more difficult to take a look at it. So I think it's worth looking at how this function would look like and how it becomes discontinuous at 0, 0. So let's graph this. Okay. Yeah, I have the other one up too. It's going to use all of them. So the function is, so you have to be careful about, because the typesetting for this isn't very nice, so you have to, watch your parentheses and stuff. Open parentheses for the numerator, x to the 4th minus 4y squared, close parentheses, start my denominator, x squared plus 2y squared. Yeah, be careful with your parentheses, right? Okay, it looks like an innocent looking function, but if you take a look at this middle part, at 0 is right where we're concerned about, right? And if you zoom in, the thing about zooming in too, it's kind of misleading, because if you try to zoom in, you're not going to get a much better picture than what you're kind of getting already. So it's harder to see. But imagine a piece of paper. If you have a piece of paper and then you fold it, just fold it and then you open it up again, it looks like a piece of paper. So that is a nice continuous thing where limits will exist. If you have something like this where the limit doesn't exist, you can't model it with a piece of paper anymore, because things get stretched out in a strange way. Okay? I don't know if that made sense. But if you're interested in diving in this a little bit deeper, I think it would be good to look at the paths going to the different places. So we define the path And let's see how quickly you can translate these paths into parametric equations. But we define the path to be x is equal to 0. Okay, x is equal to 0. And we got this thing over here, which is just -2. Okay, so I'm going to define a space curve in this program. That would be an x value. Wait, that's a parametric surface. Space curve. So my x is just an x value. So let's just call that t. My y is equal to 0 because that's what we said it was. And then when we simplified it, before we even took the limit, when we simplified it, we saw that it was -2. So if we graph this, that doesn't look right. Oh, I said x equals 0. Yeah, so 0, and then this is my t parameter. Okay, this makes a little bit more sense. So if I take a look at this graph over here, as I'm going along my curve, the red curve over here, I'm on that graph. And my graph tells me, if I'm following this path, it tells me to go along here, and I'm going to hit -2. I'm on -2. I'm just going to stay on -2. Okay? All right, now on the other hand, if we let y equal to 0 this time, which is what we did for the second path, and we let x vary, we'll let that be equal to t, what does our z look like? No, before we took the limit.
Oh, x squared.
X squared, right? So x is equal to t, so I'm going to translate that to z is equal to t squared. And then let's graph that. And that tells me that if I go along if I use my compass or my map, I want to get to 0, 0, and I take the path where y is equal to 0. So y is equal to 0. That's going east to west. If I walk along my map from east to west to get to 0, 0, I'm going to be walking along a ridge that looks like this. Okay? And by the time I get to 0, it looks like I'll have height of 0. But if I look at my compass and I walk along north-south, I'm going to be at some valley down below -2. So if you walk along east-west and I walk along north-south, when we get to 0, 0, if we're in the same place, even if there's a hole there, a punctured hole, then the limit would exist. But if you walk along east-west and I walk along north-south and we meet at 0, 0 according to the map, and I'm down 2 units below you, then we're not at the same place, so the limit does not exist. This is not a mountain range. This is a weird... Yeah. Yeah. So my analogy now doesn't make sense because the limit doesn't exist. So this is not a mountain range, a valley. It sure looked like a valley when I was walking down north-south, right? I'm walking down over here, and I'm seeing these things on the side. Meanwhile, you're walking up there, and you're going down a mountain and going back up again. But if I say, let's meet at 0, 0, and we're not at the same place, then it's not continuous. So this must be in Wonderland or something. Alice? Okay? So that's what's happening to these graphs. When you go one direction and you get there at a certain height, and you go another direction where you're supposedly at the same place, but you have a different height, then the limit doesn't exist because they don't meet. So let's see if we can identify these markers over here. So this is the, what is this one again? This is the y equals 0, right? X equals 0. So when x is equal to 0, that's the path you take, and then I see that I'm down 2 units when I'm walking there. And then on the other hand, over here, this is the y equals 0 path, and z is equal to x squared. That's this parabola right here. And then the lowest you can get is 0. And these two are not equal. And you can see that in the graph. There's a distance between them. So you can't make a discontinuous or a surface that doesn't have a limit. You can't make that with a piece of paper. What I wanted to do was bring some Play-Doh and have you guys try to make this surface, because I think it's an interesting activity to try to do.
Can you actually walk through that underlying path, or do you actually need wall?
Well, that's why it becomes not a mountain range anymore, because technically there is a wall there. But if it's imaginary, you can certainly walk through it. It's just a bunch of smoke.
But equation would work if you set conditions to it, right?
What do you mean by that?
Well, just like if you had this continuous function on a two-dimensional plane, as long as you say, well, it works from this way to this way with this number, but it doesn't, you know.
Yeah. So you can set conditions and say you can have limits possibly existing somewhere from going in different paths. But the idea is to get the holistic picture and say, does a limit exist for any path that you choose? And the answer is yes or no. And if it's no, then you're kind of done with that. Unless you do want to specify a particular path, in which case then we have limits for those paths. Unless it shoots off to infinity, then that's something else totally different. All right. Let's see if we can find some more interesting problems. Let's maybe examine one where limit does exist, but not prove it. Oh, which one is that going to be? Oh, they do one in the book. So let me do one. Let me do an epsilon delta one in the book, where I'm not going to do the epsilon delta. I'm just going to copy the function. Yeah, it's this one, I think. Actually, So let's take a look at this function. Without proving it, because the book does it, they got the limit of this thing to be equal to 0. So see text for epsilon delta proof. Why it's equal to 0, but it does equal to 0. So something like this tells you that any path that you take going to 0, you're going to be at the same level. So I take north-south, you take east-west, we're going to be at the same sea level. We're going to be at 0, we're going to meet at the same point. You take a different angle and somebody else takes a parabola path going to 0, 0, we're all going to meet at the same place. So whatever this thing might look like, it's going to approach 0, 0 at the same place. But the domain is not defined there. So let's mention the domain here. Domain, can you tell me what the domain is? I'll say, well, you say what?
When all real numbers except when x squared plus y squared is not equal to 0.
When is x squared, y squared equal to 0? When they're both 0, right? So this isn't quite correct. What do I have to fix? What? Just the domain. The domain is in 2 dimensions, so you're putting the domain are all the possible things that you can put into this function. And all the possible things I can put into the function is any pair, not just one number, not just a scalar, but any pair of numbers, x, y, except I can't put 0, 0 in because that's the only time I get 0 in the denominator. Okay? So although we're taking these different paths and we're getting to the origin, there's a hole there because it doesn't exist. It's not part of the domain. Yeah? This is a backslash, or you could put a minus sign. I guess a minus sign would work too. So it's everything in R2 except for 0, 0. So how's the graph of that going to look like? Let's take a look at it. This would be 3x squared y divided by x squared plus y squared. I wonder if those space curves are still there. Get rid of them. How do I get rid of them? There it goes. Ah, reset. So you can see that although there's something weird happening there, although there's something weird happening there, you're still going to get to the origin, 0, 0, 0. You can still manage to get there regardless of what path you take. And this would probably be one of the better shots of this graph. Where there's a hole there, but at least you can congregate there regardless of where you're coming from. So regardless of where you're coming from, we're all going to go in the same place. That sounds like an inspirational talk, doesn't it? So the limit exists. You're coming from an angle, you're coming from north-south, you're coming from a diagonal. You're all going to get there to the same place, except that there's a hole there. Yes? Probably, and probably the range is going to be all real numbers because it looks like positive and negative numbers and stuff.
And the range works the same way where it's your z-values.
Yeah, your range is your z-values. So the other point that I was trying to get to by talking about this thing with a hole in it is that there's a question about continuity. So we say that f is continuous at x naught, y naught if the limit as xy approaches x naught, y naught of the function is equal to the function evaluated at x naught, y naught. Okay. So in this case, and in the book as well, they talk about defining something in here where you would check where in this particular scenario, it's not continuous at 0, 0 because it's not defined there. Okay. Okay. All right. I have something strange for you guys to do. I need to go. But I was going to give you guys a quiz. So I have a quiz for you. This will be a group quiz that you guys can do any way you want. Because I'm leaving. And you guys can give your completed quiz to Aaron.
Pick the responsible one.
Neither of you. But he raised his hand, so. All right, so do this any way you want. You can talk to other people. You can compare answers. You can look at computers. You can look at your notes, your book, whatever. Just do the quiz and then give it to Aaron, and then I'll see you guys tomorrow. There should be more quizzes, yeah.